Hi everyone, my name is Karel Bartos. I'm a researcher from Cisco, and I would like to show you today a new way how to represent network traffic so we can detect new and previously unseen malware variants. So a little bit of motivation. Every day we see a large variety of malicious samples, and to detect that we need a lot of labels. And we don't have that because obtaining additional labels is very costly. So the current security detectors rely heavily on signature matching, feeds, blacklists, and those things. They are fine, they have a really good precision, but their ability to detect new things is very limited. And what's worse is that the behavior changes introduce problems when we want to train the detectors. So HTTP or HTTPS is heavily used by the attackers for a large variety of attacks. And some of them follow an escalation path, which means that they initially start at, for example, as money scam or ad injector. Some of them can advance and use exploit kits to get to the terminal stage where the damage has been done and there is no turning back, which is exfiltration or ransomware. And our goal is to detect all of these threats with our representation, and the representation should be invariant in terms of, okay, we can detect current attacks, but when an attacker will change something, we will still be able to detect that. And the most typical changes we see are the following: the change in the malicious code, payload, or obfuscation. It happens all the time. Change in hostname or server IP address to bypass the blacklists, right? Change in the intensity of the attack, in timings, or in the components of the URL. Everything happens very frequently, and we want to build a representation that is invariant against those changes. So our input data is, we use proxy log records, which are basically information from the header of the packet, and it's a metadata with the fields like time, IP, URL, user agent, MIP type, and those things. And I will be referring to one flow will be for me one row in these proxy log records. So basically one flow is one connection in this data. And I will be very frequently using the word bag, which is actually a set of flows with the same user or device and the same host name. So it basically describes the communication between one user and one host name. And what we did, we took all our malicious traffic that we had and divided that into three groups. The first one is called single flow bags, let's say. And those bags are single flow communication from a user to one domain. So those bags have only one flow for a long period of time. It could be basically some unsuccessful attempts when a DGA domain, or if a malware wants to contact a DGA domain that doesn't exist or something like that. So those bags are not that much interested. Then the second one is more interesting. Those bags are static bags where we can observe more flows, but all of them are the same. So it could basically be something like a CNC channel where the channel asks what to do with the infected machine. And finally, the most interesting category is the dynamic bags, where we can observe different flows in the communication between the infected user and a domain. And this is what we actually are focusing on, because the single flow bags or static bags can be modeled by standard and widely used flow-based features, which means that you will take one flow, extract a predefined set of features, put it into the classifier, and that's it. And since all of the flows are the same, there is like no way how to use the other features. But in case of the dynamic bags, it doesn't. I'll show you that it doesn't work, and we need to define a new representation that is based on the bag itself and not on the individual flow. So let me show you a simple example. Here you can see two bags of malware sality, and the question is, are they similar or different? So if you look at it from the flow-based perspective, you would say they are different because they have different host name, different path, different file name, different parameters, right? So if we make it really simple for an illustration and see, okay, we have one feature which is a URL length, and we will use it to classify these two bags. For the first bag, we got 5 numbers. For the second one, 5 numbers as well. We will put the first one into the training bag, the second one into as a testing bag. We will learn a model based on the training data that if the URL length is between 44 and 48, it means that it's malicious, but the testing bag is not detected because the length is more than 48. And you can say, okay, that's a very simple example, right? I agree. But we did much more investigations here, and we analyzed many malware categories and many flow-based features, and this is exactly what happens. So on the illustration, the rows represent malware categories, and the columns are features, and the color represents the variability within the category for this particular feature. Yellow means that all of the values are different, while the blue color represents or means that all of the values are the same. So the most variable is a URL string itself, which is not surprising, right? But what this illustrates is that it's even hard to actually learn a flow-based classifier for one specific category, not mentioning a classifier for all of those categories together. So we should be using something else. So, all right, we can use a histogram, right? So we will predefine a number of bins and put the flow-based feature values in the histogram and get this feature vector. Let's say we have 4 bins for simplicity. We'll do the same thing for the testing bag, and we got much better result, but the question is, okay, is it enough or not? So we thought, okay, let's find something even better than that. And we want to ask ourselves, what is actually the thing that we want to represent? What is the common thing across the malware categories? So here is, you can see a few examples of different malware bags and 2 examples of legitimate traffic. I hope you can read the exact characters, because then you would be focusing on the flow-based features, and that's what we want to avoid. But if you have a look at it from distance, you would see that, okay, the malware bags or the flows within the malware bag look very similar, and this applies to every bag here, as opposed to the legitimate traffic where the flows or where the URLs are actually very different, right? Because you have to download, if you go to a legitimate page, you have to download some JavaScript, some pictures, some frames, right? And so on and so forth. So the URLs are different. And this is exactly what we want to extract here, the URL structure of the malware bags, or in other words, the malware dynamics. And how we are going to do that? Well, we can see a parallel in action recognition when you have a sequence of images and you want to detect or recognize some kind of action. So for us, one image is basically one flow, and the video is the sequence. It is the bag. So the bag actually describes a video of malware, and we want to detect that. So what is commonly used in action recognition is self-similarity metrics. So we compute from the flow-based feature values a self-similarity matrix, which is a matrix where, for example, at the first flow, you have in the first component there's a difference from the first and the first, then the difference between the first and the second, first and the third, and so on and so forth. So you get these metrics of the differences, and it actually describes the dynamics, and it describes what we need. So if we do this, and okay, it's symmetric, right? So we can take only the lower triangular matrix of this, or the upper, it doesn't matter, and put it into the histogram again, and got the feature vector. And surprisingly, if we do this for these two bags, the feature vectors look the same, or they are the same. So then we can combine it with the original histogram, and we have our representation. And with this representation, we can actually detect all versions of Sality. But not only that, we can also detect CryptoWall, which is a well-known ransomware, right? Because as you can see, it has exactly the same variability. It has exactly the same dynamics. We can detect DNS changer. Actually, we were the first who detected an large DNS changer outbreak a few months back. We can detect exploit kits, like this RIG exploit kit. You can see that, okay, we have several URLs with tons of nonsense traffic, or tons of random characters. We can detect redirects, and we can detect many other categories. So this is the overview of the process of getting the representation. So at first we have the flows. We will group them into the bags, extract the flow-based feature values. For each feature, we get all the values and compute the histogram, compute the feature differences, again histogram, and all of this is concatenated into the one large feature vector. And this representation is actually invariant against all of these changes the attacker can make to bypass the current security. So, okay, we are using metadata, so we are invariant against any malicious code, payload, obfuscation, and so on. It goes by default, right? If the attacker if the attacker decides to change the server host name, it will just change one part of the URL, but the structure will remain the same. So no problem. If he decided to change the URL path or file name or number of flows or thinking time, ordering, number of bytes, doesn't matter. We're still able to detect that. Of course, there are some limitations, and I'll show the limitations here. So I said that we are modeling only the dynamic behaviors, right? So if we observe only one flow, or if the flow is repeating itself, it has zero dynamics, so we can't detect those. If we observe multiple behaviors in the same bag, so the bag contains like a mixture of various behaviors, it has a violated dynamics, and it will not be detected as well, but we don't see that very often, because that would mean that you would have more behaviors from one user to one host name, which is like very unlikely. Then HTTPS, right? So yeah, we are using URLs. We don't have that with HTTPS, so we are currently working on how to make it work only also for the HTTPS, and this is a work in progress. So this version doesn't work for HTTPS. And also, if the attacker decides to create a malware that would really dynamically change the behavior, that would also decrease the performance of the method. So that was the representation, and as you saw, it heavily depends on the histograms. And if you create a histogram, you have basically two parameters: the number of bins and their width, right? And usually, what you do if you want to apply a histogram, you just say, okay, so let's define 16 equidistant bins and see, right? But that's very ineffective. So what we did, we actually invented a new way how to learn the number of bins and their widths automatically from the data, so it is optimal for the classifier. And this could be applied not only in the domain of network security, but in the other domains in general. And I don't want to go into the details, but I'll show you the basic idea. At first, you define a large number of small equidistant bins, let's say hundreds of small bins. And then you start iterating and start evaluating the classifier with those bins, with this representation. And you start merging those small bins into larger bins. And two neighboring bins are merged if both contribute to the same class, which means if they both contribute either to malicious traffic, to recognize the malicious traffic, or to recognize the legitimate traffic. And at the end of this iteration process, we ended up with a handful of bins of different widths and different sizes, exactly optimal to our problem and to our classifier. So I'll show you let's jump into the experiments. We took all our data that we had and separated into the two data sets, the training data and testing data. And for the training data, we used 8 malware categories and a background traffic of company A, let's say. And the testing data contains 24 completely different malware categories, completely different from the categories that are in the training data. And a background was a different company. So it is like the toughest scenario that you can have. Here is the, okay, so it doesn't display very well, but it is an illustration, a two-dimensional projection of the flow-based feature values and our proposed representation. And on the left-hand side, you can see that the flow-based feature values, the malicious traffic is distributed all over the place, right? So you can't build a classifier with the flow-based features or general malware classifier with the flow-based features. But what you can do is to actually, you can see that there are some small red clusters. And each cluster is basically one malware behavior. So with the flow-based features, which is the baseline, you should be able to learn one specific classifier for one specific behavior, but not the general one. As opposed to our representation, where the legitimate traffic is like separated from the rest of the malicious categories. Here you can see the how the bins look like. And if we use a standard SVM algorithm and learn the bins like as a baseline, you can see that the histogram, this is actually how the representation look like for the one feature. The histogram is a chaos. It has a lot of bins and they are chaotically going down and up, and this will really result into overtrained classifier, as opposed to the our method that actually learns the number of bins and their sizes, and we ended up with 18 bins for this feature, and they are of different widths, right? And here you can see what is the effect of this. So if you have the original histogram, which is like a chaos, you can see that the decision boundary is very complex and the classifier will be overtrained. While after applying our approach, the number of bins make it much more smoother and and it will actually increase the generalization of the classifier a lot. So here are the final efficacy results. On the left-hand side, you can see the ROC curve in a log scale. And the yellow line represents the baseline, which is the flow-based feature, which is a classifier based on the flow-based feature values. You can see that it has very unsatisfactory results, as opposed to the 3 lines, the blue, green, and purple, which are the proposed representation describing the malware dynamics, but with the predefined number of bins that are equidistantly distributed. And if you apply the other method that actually learns the histogram and the number of bins, you will get the red curve, which is in order of magnitude better than everything else. And if we have a look at it from the security perspective and plot the precision recall curve, the optimal point, I would say, is around 90% precision and 67% recall, which means that the classifier was able to learn 70 or 67% of new malware categories, was able to detect 67% of completely unseen categories with 90% precision, which means that out of 10 alerts, 9 of them are actually malicious traffic. So to conclude, I showed you that the flow-based representation is not very suitable for making a general classifiers, and we need to invent new representations. I'll show you an example of such a representation describing the malware dynamics, and also which is further improved by another algorithm that learns all the parameters of the representation automatically from the data, so there is no need to manually predefine anything which is completely unoptimal. And as a follow-up, we would like to make it work also on the HTTPS, which would be really awesome. So that's the end of my presentation, and thank you.
Hey, very nice work. I'm Inchen from Qualcomm. A quick question. How would you approach HTTPS?
Yeah, well, this is something that I cannot answer yet because for various reasons. But I can only say that you should probably you should redefine the bags. And you should use more contextual information, and that's everything that I can answer you.
Thank you.
Hi, you commented on the point that you found to be optimal in terms of trade-off between precision and recall.
Right.
But normally, especially if you're alerting on flows, in a normal company you would have a very large number of flows, so you would have to tweak your detector to have a smaller amount of false positive. So can you comment on other
Sure.
trade-off points?
Actually, the metric was not based on the flows, but on the level of bags, which means the user hostname communication. So this is basically the malware activity that we can see on the host. So it describes the number of infected users, sort of. So that should be, I think, quite okay for alerting based on at the level of users, right?
These pairs should still be a very high number in a normal. If you take a Fortune 500 companies, how many bags would you expect?
Well, we see hundreds of thousands of bags, but I didn't show you how many malicious bags are actually found at the company, right? I'll show you that out of 10 alerts, 9 of them are malicious. Which is kind of the actionability that you would perceive if you have this kind of detector.
Thank you.
Okay, let's thank Karel again.